We need to outline methods for measuring the half-life of an isotope. We'll start with short half-life. With a short half-life, it's relatively easy. We need to plot a graph of the activity against time, and we can just measure off what is the half-life. Start at 100, goes down to 50, the half-life is 25. Let's go from 50 to half of that, 25. Between 25 and 50 is 25. Half of 25 is 12.5. Between 50 and 75 is 25. So do that directly. For short half-lives, we can find the half-life directly, and then we can work out the decay constant from that. Let's do an example. You have a radioactive sample where the initial activity is 50 becquerels, 50 decays per second. After half an hour, it is 20 becquerels, which is a little bit less than half. So how do we find the half-life? We start with the equation n is equal to n naught e to the minus lambda t. If we just divide this by time and divide this by time, we basically have the activity at a particular time is equal to the original activity times by e to the minus lambda t. So we just substitute for the activity equation, which is a, the activity after time t, is equal to a naught, initial activity, e to minus lambda t. So we use the equation where we find the values for initial value and the final value of the count and the time in seconds. So we know the activity to start with is finally is 20, initially it's 50. What is the total time? It's going to be 0.5 hours times by 60 times by 60 is equal to half of 3,600, which is 1,800. Now we need to rearrange the decay equation and substitute values to get the decay constant. This is the decay equation, so we just put those values in. We know A naught, we know T, so we're going to find a value for lambda, which is 5.09 times 10 to the negative 4. Then we substitute values, this value of lambda, into the half-life equation, and we're going to find that the half-life should be equal to 1361 seconds. Does that make sense? We know between 50 and 20, that's more than a half-life. It's more than half an hour, which it is. So that kind of agrees with this value. But you should be able to do this yourself. When we measure long half-lives, the method is a little bit different. Uranium has a half-life of roughly 10 million years. These are very long half-lives, and it will take too long for there to be an appreciable change in the decay rate, so we can't wait long enough for there to be a difference in the decay rate to be able to find out how much the decay is decaying. The decay curve is almost a straight line, and we can't really detect any difference. Now, if you know the rate of decay by the number of particles that decay each second, and you know the value of n, then directly you can find out lambda. Remember, this is the decay rate, this is the original number, or at that time, and then we can find out lambda. So we need to know the number. So in other words, we need to know the mass of the substance to work out the number of atoms that we have. We also need to know the decay rate, and that will be using a Geiger counter, and it will count the number of disintegrations per second. So here is an example that we looked at before, where we have a sharp decay curve here, but with a very long half-life. This is such a straight line, we don't know, we can't be around long enough to detect when it's actually going to be coming down to half the value. So we have to use this method. So with long half-lives, we must count the decays and compare to the number of nuclei. Okay, so delta n divided by delta t, the decay rate, is equal to lambda n, or negative lambda n. So the rate of decay depends on lambda, and the number of particles at that time. For example, if we have 10 to the 23 nuclei and the decay rate is 100 becquerels, which means 100 disintegrations per second, using this equation, delta n divided by delta t is equal to lambda n. We substitute the values. We know the decay rate is 100 becquerel. We know the number of particles is 10 to the 23, so it's going to be 100 is equal to lambda times 10 to the 23. So we rearrange to get lambda, and we find lambda, the decay constant, is equal to 10 to the minus 21 per second. Another example for you to do is if we know the activity is 3000 becquerels, we need to find 2 grams of that element of a mass which has 235, and that's only basically 2% pure. So we have an element X which is 235. We want to find 2 grams of this material, but only 2% of it is the nuclide which is decaying. So we need to find, given that we have 2 grams, how many particles are in 2 grams, given that the atomic mass is 235. And then we need to find 2% of that. So how many particles are uranium in this? Then we use that equation to find the decay constant, if we know what the activity is, and then we can find the half-life. You could try to do this. This will be on the reading quiz. This is another question you could try. The wood in a living tree contains the isotope carbon-14. When the tree dies, the amount of carbon-14 in the wood from the tree decreases. The half-life of carbon-14 is 5,700 years. Deduce that the decay constant of carbon-14 is 1.2 times 10 to the minus 4 per year. You can do this in terms of years and don't convert to seconds. Just stick to years and the units will work out. You should end up with a value for the decay constant of 1.2 times 10 to the minus 4. The activity in 1 gram of carbon-14 of the living wood is 0.24 becquerels. This ancient bowl has, of the same type of wood, has 0.075 becquerels per gram, and this is also per gram. So we need to determine the age of the bowl. So use the equation to find out how many, the ratio by which this is changed, and then we can find time because we know what the decay constant is. You should end up with a value of 9.7 times 10 to the 3 years as the age of the bowl.